So officially, thank you everyone for coming. Welcome back to the Python for Operations Research webinar series of workshops. Thank you so much for being here on the third installment, where Christina is going to guide us through how to use Gurobi with Python. So without any further ado, I'm going to leave the floor to Christina, who's going to teach us a thing or two.
Thank you so much, Rose. So after some technical difficulties that we all need when we want to start a Zoom presentation, I am very happy to be part of the third installment today again. As Rose already said in the first time when she introduced the four of us, I am a PhD candidate at the Technical University of Munich, and I got to know Gabriel, Rose, and Oikü during my time as a visiting researcher at the beginning and middle of this year at the Sirelt, and it was a very nice time. I really enjoyed it here. And now I'm very happy to be part of the presentation. I will talk to you about Python and Gurobi. Gurobi is actually in some way the further development of the program we were talking about last week, Cplex. The founder and two of the main employees of Cplex actually founded Gurobi, which is the abbreviation of their last names. So basically we're doing something better, and even the founders of the former program were actually thinking that Gurobi is better than Cplex, but this is just a personal discussion that we can maybe have later on. And my iPad does not like me, so I'm going to share the screen here and we'll just use the normal presentation. So you will be missing all my cool annotations, which I'm sure that everybody can live without. So I'm going to share here. As I said, there will always have to be some technical difficulties. I hope you can see my screen now. Someone?
Yes.
That's good.
Yes, we
can. Answer? Okay, thank you. So let's just dive right in. Rose already sent out the installation instructions, and I hope that most of you already have Gurobi running in your Anaconda. So basically, we already know how to install Python with Anaconda and how to actually work with that. And then in order to have Gurobi running in the background and helping us optimize things, we want to add a Gurobi license to Python or to the Anaconda environment. This is later on for you again to walk through if you haven't already. And then there is some basic way how to use your platform with the Gurobi optimization software. And then in the end of the slide, you see an interesting link. That's actually a webinar from the people at Gurobi, where they show in a nice video format how to use Gurobi and Anaconda together. It's basically similar to this workshop, but not as interactive, of course. Then let's start. How do you actually optimize or model something in the Gurobi Python interface? What are the parts that every model needs to have when you want to work with it? So we iterate through this with a very simple mixed integer problem. And this example formulates and solves the following model that you can also find within the Gurobi documentation. Generally, I would suggest actually really having a good look through the whole Gurobi website, through the documentation, and through some other links I will later on present to you, because I think they have been doing a really good job in actually showing you and guiding you through how to use the software. And there's a lot of examples. There's also a lot of workshops and other things and presentations that they have uploaded up there. So it's a really good source of information. So basically, in a general way, we want to optimize this model. We want to maximize the sum of x plus y plus 2z. Then we have two constraints, and all three of our decision variables are binary. This is the thing we're working with. It's a very simple example. I will later on introduce a little bit more difficult model, and then you will have 2 to 3 examples that you will be able to code that are even more advanced. So basically, at first, we need to import the Gurobi Py module. The Gurobi Py module imports the capabilities to perform your optimization with Gurobi. So it contains Gurobi functions and classes. If you have not imported this, you won't be able to use the optimization software PyGurobi within your Python shell. If you remember the first session where we were talking about modules, it's a good idea to define the Gurobi Pi with the short abbreviation GP to later on save time during the modeling process. So basically, you import Gurobi Pi as GP, and from Gurobi Pi, you import GRB. So what is GRB? That's a class from within the module Gurobi Pi that has additional Python constants. So the classes, for example, GRB attributes and GRB parameters are used to get or set Gurobi attributes and parameters respectively. You will be seeing the GRB as well as the GP abbreviations later on during the modeling process. So then now we actually need to create the model. The process in here is that we start with a new empty model, and then later on, that's just general use. So you start with a new model, and then later on in the next steps, you add the constraints, the variables, the objective function, the constraints, and everything else that you actually need in your model, and then you run it. So we use the Gurobi Pi function model. So basically we print Gurobi Pi.model, and then we name our model something. You could call it Christina, you could call it MIP1, as we do here. And later on, if we want to refer to this model, we give it the name M, which is basically like a variable or a reference point. So later on, when we want to add things to the model, we will always refer to it as M. But the name, which is something that you can change to be a more insightful variable or name than M. So that's why we call it MIP1 here. So if you think that you maybe want to have an updated version of the MIP, then you can call it MIP2, and you won't be confusing yourself which version of the model you're actually working with. So now we want to add decision variables. If you remember, we have 3 decision variables, X, Y, and Z. That's a pretty easy and straightforward approach. Generally, we add variables through the add_var method. If more than one variable is added at the same time, we can use add_vars. So this is the plural, just basically take a look and be careful which one you use, because it can save you a lot of processing time in your head if you actually decide correctly in the first place. I had a lot of problems with that once. Each variable has a type and a name, and it has some arguments. So the add_var method can take some arguments. It always needs indices should you be using indices. So for example, by definition, if you add variables more than one variable at the same time, so if you use the add_vars function, you will be needing indices for your variables. For example, you want to iterate over all I in I, then you need to put this indice into your add_var method. You will be able to define lower and upper bounds, as well as objective coefficients for your new variables, and you will be able to define variable types. The 5 different variable types that Gurobi offers are the continuous, the binary, the integer, the semi-continuous, and the semi-integer. And then obviously you will also be able to give it a name. And this will be subscripted by the index of the generator expression. This means that if you add a variable and you iterate over I, as I already said, and you call the variable capacity, then you will be having capacity 0, capacity 1, capacity 2, up until your capital I, that is the end of the indice set. And here you need to remember again, it's also something we were talking about in the first session, that the indication of sets in Gurobi starts, in Python generally starts with 0. So the first item will not be 1, it will be 0. And then we do this for our problem. So we add var, because we only have one X, one Y, and one Z variable, and all of them are binary. To be able to distinguish between them, we will have the names set as well. Then we want to add an objective function to our problem. we want to use the function setObjective, which takes 2 arguments. The first argument is on the left side of the comma, and the second argument is on the right side of the comma. You see here that on the left side, the first expression is the first argument, is the mathematical expression of your objective function, which you're just typing out as is. And then secondly, the second argument is whether we are dealing with a minimization or a maximization problem. Here we need to use the GRB and then just all capital write maximize or minimize. Then you see again that we refer to the M, to our model. Within the empty model, we now place or set an objective. Then we also need constraints. We've had 2 constraints that we need to worry about and that we need to add to the problem. You can use the add constraints method on the model object. So again, referring to the M, then we add the constraint. Then we also again have 2 different arguments that this function takes. On the left-hand side, we have the mathematical expression of the model, everything complete with the smaller or equal, or the larger or equal sign. So you plug in both the left-hand side and the right-hand side of the mathematical expression. And then you can also name your constraints. This will later on be very insightful when you want to refer back to which constraint you're working with, when you maybe want to not include a constraint and see how your problem solves or anything else. So basically naming things in a way that you're able to refer back to them in general is a good coding practice. And it's also recommended to not be confused when you have a very large problem with a lot of constraints. Then Gurobi is already evading to update the model. So Gurobi is running for it. But I want to have a small remark in between here. As you might have seen, we have very simple constraints in here. Most of the time, once you build a larger and more complex model, you will have larger and more complex constraints and objective functions. You will eventually need to use a summation function. There is the sum function that we already were talking about when we were talking about the general way that Python actually sums up things in the background. There is the quick sum, which is from within the Gurobi Py module that the people at Gurobi defined in order to be able to deal with large expressions of var objects. So basically, if you want to sum up something that is really large, a large instance set, items within sets, or dictionary keys or something like that, then you will be using the quick sum. Basically, for example, here, you can just use the quick sum of the expression of the factorial for those items in this range. This would be too little. In here, you won't see a computational benefit of actually using quick sum instead of sum. But generally, I wanted to talk about this because when you, for example, look at the Gurobi examples that they upload on their website, you will be seeing the quick sum a lot of the times. And I just don't want you to be confused when you read this, because it's basically the same functionality as the normal sum version. So now we finally have finished building our simple model. And the next step is to run the optimization using the optimize routine. You optimize the model M, and then you put the optimize function in here. It doesn't take any arguments, so you just run it like this. If you don't tell Gurobi to not write all this output down for you, you will eventually see everything that you read here in your console. So if you use the Jupyter notebook, it will print out like this. You can also run it in your notebook in parallel, which I hope you do, because the notebook is very helpful to understand everything. Or if you use Anaconda, this will also print out to your terminal. The informations, I think, are in the beginning very insightful. If you actually rerun your model all the time and you already know that it works, you can also mute this and you flag the output of the model to equal 0. But that's something that I would refer to later on, or that I would just do when I already know that my model works and I understand everything that the model is actually doing. So for example, you see here that the variable types, we have 3 binary variables. We have a pre-solve time of 0 seconds. we don't need to explore anything because we don't need to iterate through the simplex. And then we have a solution count, and an optimal solution was found. The best objective is 3, and the gap is 0. So for example, if you were to program something that would time out your optimization after a certain amount of time, you would be able to see the gap value here relative to the optimal solution. Okay, we have done something, but we want to analyze it as well. So we want to find out what are the variables values after running the optimization. So we can print out the names and values of the decision variables by using the .var and the .x, the .var name and the .x variable attributes. So attributes is something that is inherent with some data type that you have introduced within your programming problem. Variables can have attributes, and the model itself can have some attributes. So variable attributes mainly are the var name and the value .x of the variable. So you can just iterate through the variables within the model. This is another function. It's the getVars function that will just, if you run it on its own, it will just print you all the variables that you're actually dealing with in the problem, but in an ugly way. So in a way that Gurobi or Python understands it. But if you actually want to make it readable, easier for you as a person, or for your students, for your supervisors, for your mathematical discussion in the paper, you can just print out the variable name and then the value, and then you will see it like this. So for example, in our problem, the binary values x and z are set to 1, whereas y is still 0. And then we can query the .objective value attribute on the model. So we will be putting down model.objective value, and it will print out 3. And if you remember here, we also saw that the best objective is 3. So we're right, and everything works just as we were expecting. Generally, I refer back to the documentation once again, because I think the attributes are also explained very nicely there. And then, as I said, models and variables can have attributes as well as constraints and the solution quality itself. But for example, things that I use a lot of the time within the model attributes are the number of variables, the number of linear constraints, the number of binary variables, the current relative Mip optimization or optimality gap, as well as the runtime for the most recent optimization. You don't have to be scared that Gurobi doesn't really understand what you're meaning with runtime. I had a long discussion with a colleague of mine this week about the runtime, and it's actually really smart because it won't take any of further iterations into account. It will just generally be the time that it needs to compute your solution. And then some interesting variable attributes are the lower bound, the upper bound, reduced costs, or the unbounded array of introduced variables. But generally, there's many more. You will find all of them in the Gurobi documentation, should you need them. Okay, now a bit more of an advanced modeling example. I took this from the introduction to the Gurobi Jupyter Notebook modeling examples. There's a bunch of them on the website, and I think they're really nice to actually click through and understand what the modeling looks like and how very efficiently modeled code looks like in Gurobi with Python. We will be talking about key components in formulating a Mip problem. Basically, they will remind you a lot of the things we were talking about in the very simple example, but we will just have some more information, and I think it's nicer to see another approach as well. So let's get started. The problem description. We are a consulting company and we have 3 open positions we want to fill. We search for a tester, a Java developer, and an architect. We have 3 top candidates, also referred to as resources for those positions: Carlos, Joe, and Monica. We have administered competency tests so that we know how competent each candidate is for each job. We will be having 1 value for all 3 positions, determining the likelihood or the performance that each of those 3 resources have. We will call those values matching scores, and you will see them later on. Only one candidate can be assigned to a job. So we don't want to have 3 testers and 0 Java developers and architects. And at most, 1 job can be assigned to a candidate. So for example, if Monica were to be really competent, she still won't be able to do 3 jobs. So we just want to have 1 person at each job, and we want each job to be filled. The problem is to determine an assignment of resources to jobs such that each job is fulfilled. Each resource is assigned to at most 1 job, and we obviously want to maximize the matching scores of the assignment. So we want to have the optimal solution for the company. This might mean that, for example, Carlos is more likely to be or better performant in the Java developer role, but the optimal overall solution will assign him to be a tester. Let's start with the implementation, shall we? The following Python code imports the library of Gurobi Pi as GP again, and it also imports the GRB class into the main namespace, so into the place where we are optimizing. Generally, I just want to add that the GP abbreviation for Gurobi Pi will be the one that you will be seeing when you Google, when you refer to Stack Overflow, basically when you look up anything related to Gurobi and Python. And sometimes people, for example, on Stack Overflow, will be assuming that you know that GP abbreviates Gurobi Pi, and they won't be using this import line when they show you their minimum working example. So just to be aware of where the GP dot comes from when you refer to any of those resources on the internet. Then we formulate the problem, which is a resource assignment problem, where we have a list R that contains the name of the 3 resources or potential employees, then the list J that contains the name of the job positions, and then R element R is the individual resource, and J element J is the individual job. In order to set those up, we define 2 sets. If you remember our first class on how to define sets in Python, you will remember that the sets are very simple. You basically can put in any type of variable. And in here, we're using strings, which we identify by the actually, I don't know what those are called in English, but you know what I mean. And you index them by those little tiny commas up in the air to make sure that these are strings and that you will have Carlos and you will be able to actually read his name when you refer to the instance that you index with R in capital R. So here is the ability of each resource to perform each of the jobs. As I said, they're different. They don't add up to 100 because each of them is individually capable of performing the jobs. And this is the matching score S. In the Gurobi Python module, we can have, or we are introduced to a function that is called Multi-Dict. It's basically an improvement of the dictionary function that we were talking about when we were talking about the basics of Python. And you can use it to initialize 1 or more dictionaries with a single statement. The function takes a dictionary as its argument, and the keys will represent the possible combinations of resources and jobs. Basically, this is the case in here. As you see, we need to look into the GP module. Only then we're able to use the multi-dict function, and we will be able to match the combination of a resource and a job with the scores that are assigned to that. Again, resource, Carlos, job, Java developer. Poor Carlos is only 27% able to perform the Java developer job. And this multi-dictionary is now our option to actually later on refer to those 2 combinations or to those combinations of those 2 individual sets, basically the individual items within the sets and their corresponding score. Obviously, as always, in programming, you will be able to do this different ways. It doesn't mean that this is the only efficient way, but it's the way that the Gurobi people decided to introduce this problem to us. So I would assume that if you had a similar problem, you will be doing well when you just follow this example. Then we also, as we did before, need to declare and initialize a model. We abbreviate this model by ARP, which is for the resource assignment problem, but we still want to have the M whenever we refer to the model, which is just a general thing that people have agreed upon or have seemed to agree upon, because it's shorter than just writing model the whole time. Again, we are declaring an empty model that doesn't contain any information, and later on, we will be adding all the other important things. So the first thing that we add are the decision variables. The decision variables are binary variables because they will tell us whether a resource is assigned to a job. So if the variable x11 equals 1, Carlos has the tester job, and correspondingly with all the other values. This basically is a very simple way to declare or to create those decision variables, because we just use the model reference, add the variables, use the plural description, so we add wars instead of add war, and then we just use the combinations, which we were declaring beforehand in our multi-dict function. And we call these decision variables assign. If you remember correctly, we do not assign this to be a binary variable, because this, in this case, is the default way that Gurobi assigns the value to the decision variable, the type to the decision variable. But you can be like on the safer side if you actually write down grb.binary just to make sure. It's also just something that I like to write down, even if I know that it will be binary anyways, just to be able to quickly check it and to quickly read over your introduced decision variables. Then after we have our decision variables, we can introduce the constraints. The first one is the job constraints, or are the job constraints. We know that each job needs to be filled. The company needs a developer, the company needs a tester, and it needs an architect. So summing up over x11, x21, and x31 needs to be 1. Yeah, we need a job. We need people to work on this job. And it needs to be exactly 1, as in this mathematical formulation, because we want to make sure that we don't fill the same job twice, just because people are very likely to be able to perform well as a Java developer. We don't need 2 of them working this job. We need 1 person at this job and at each job. Again, we use the add constraints in the plural version because we have multiples of those for each of the jobs. So for each J in J, so basically we will be creating 3 so-called jobs constraints. Here you can also see the name on the right. So the first argument that this add constraints function takes is the expression. So we sum up over the X decision variable over all resources, which is what this expression tells you. So it's just taking all the resources, and then for each job needs to be 1. If you go back to this expression, we take all the resources 1, 2, and 3 for x11, x21, and x31 over the job tester, so over 1, need to sum up to 1 overall, which basically is what this job constraint tells you for each and every job written down. And then on the other hand, each person is only available once. So the resource constraints will tell you that summing up over x11, x12, and x13 is at most equal to 1. So basically, this gives us some slack in a sense that you will be able to maybe not assign a person should they be really bad. But in the end, the other constraint will probably override this because we need every job to be filled. We have 3 jobs and 3 people. So basically, because of this, you will be able to assign each person to a job. But should we, for example, have a 4th person who has no idea about programming whatsoever, they won't be assigned. And then we create the resource constraints, which look very similar to what we were looking at beforehand, because we add constraints again for each resource in the set of resources. We name it resource, and we sum up over the X variables for each resource over all jobs. Basically, it's just the other way around. If you remember also the table in here we look on the availability, which goes down for each row. And on the other table, we were looking at each column individually summed up. So this kind of also shows you how those 2 constraints relate to each other. Then finally, we need to add the objective function. As we were already talking about, we want to maximize the total matching score of the assignments so that the jobs are done in the best way possible. Basically, we want to make sure that the company has the best combination of people for the jobs that they want them to do. The jobs are actually determined, or the likelihood or the potential that the people show for a job is actually again shown by the matching score. And we just want to multiply the matching score with each of the binary variables and then sum over all of those. So the matching score times the binary variables summed up over all resources, summed up over all jobs. Here again, we use the model set objective method. So we refer to the model that we call M. Then we say set objective. And then if you remember, set objective takes 2 arguments. On the left-hand side, the value of summing up over all the scores. So the product over all the scores times X. And then on the right-hand side, it's the GRB maximize function because we want to maximize our overall scores. And then we use the write method, which is something that I find very helpful, especially at the beginning when you're developing a problem, to write your model formulation to another file. This file is called whatever you want to call it, but you may need to make sure that the extension of the file is LP, which you might already know that LP normally refers to the phrase linear program in operations research, and which is actually what we're doing here. We're all talking about linear programs today. And in general, that's the main use that we have for the Gurobi optimizer in this case. And if you write this in this way, so you say this model, please write it down as the file name arp.lp, you will get the file, the LP file that you're able to write. Sorry, I just muted him because I can't hear myself thinking. So the LP model is, or the LP presentation of the model is then saved in this file that, for example, when you're working with Anaconda, it will show up in your file overview, and you can just click on it and it will open in Anaconda and you will be able to read all the information on your model. For example, here you see the model is called RRP. It's in the LP format. It's a maximization problem. It will show you the maximization, like it will just write it out, and then it will show you the full formulation of the objective function. Then it will show you what it's subject to. Here you see that we have 3 job constraints and 3 resource constraints. And here you also see the reason why, when we defined the sets of the resources and the set of the jobs, we were calling them Carlos, Joe, and Monica, tester, Java developer, architect, because now those speaking names actually enable us to be able to read the constraints. If we were calling Carl, or we were referring to Carlos, Joe, and Monica as 1, 2, and 3, it would be hard to remember which one was which, and to remember whether we did assign the matching scores in the correct way. And so now we can just really have a look and we know what we're talking about. If we were having any bounds in our problem formulation, those would also show up. And then the LP file will end with the word end. Another interesting thing that you can later on use once you optimized your model is to use the m.write and then use, instead of the LP extension, the SOL extension for solution, where you will actually see the list of all the decision variable values. So you will see the name of the decision variable and then the value that resulted from the optimization run. This is also very interesting if you don't want to print it all to your terminal, but you want to have it saved for maybe later on doing some post-processing, doing some further dive into what your problem actually solved and what it did. However, both of those methods result in very lengthy files once you have a longer model, a more complex model. So you need to basically judge whether it's worth printing it or not. And then finally, we optimize our model. We run the optimization engine starting m.optimize. And then again, you see the printout that we will get when we do not flag the printout to be 0. And we know, or we see here, that we were using 5 iterations in the background to solve the problem, but we were able to do so in a very quick way because it's 0.01 seconds. And then we were given the optimal objective that is 193. So basically, you just need to move move the dot 2 spaces to the right to be able to see that. But if you wanted to have that in a more visually pleasing manner, you could also do you could also print the objective value as it's done in this way, and also you can print the variable names and the values. In this case, there is another if condition in printing it. If you remember when we were talking about the first model, we were only using the 4 v in model get vars, and we were not worried about the values. We just wanted to print all of them. But here we already have 9 combinations. So we have 9 different decision variables, and it might get not with 9 particularly, but if you have more of them, you might not want to print all the binary ones that only take a 0 value, but you only want to say, okay, those take a 1, and I just want to print those out. So this is what's carried out here. So we see that the assign value for Carlos and Testa, for Joe and Architect, and for Monica and Java Developer are 1. Basically, this means that those people got those jobs, and that overall we were able to achieve a total matching score of 193. This concludes the second example that I wanted to provide, and now I still have some additional insights that I would like to share with you. Overall, the Gurobi log, it's the thing that is printed out on the screen that we saw, as well as in a file that's named gurobi.log. It will automatically produce this, and it will allow you to track the progress of your optimization. The log will have multiple subsections giving informations on the simplex, the barriers, the MIP, the solution pool, and much more. Obviously, whether those informations are relevant to you or not depends on the optimization problem you're dealing with. So basically, just be aware that Gurobi already gives you a lot of information just by running the optimization. And if you want to find out more about the log, I again refer to the Gurobi documentation. Something that you might forget, or that I at least forget sometimes, is that while I am optimizing with Gurobi, I'm still optimizing in the Python language. So if I want to do some pre or post processing, I can still use all the functions and all the functionality that Python gives me and that is introduced with dealing with the Python language. So for example, you can use functions that you set up with the def keyword, and then you need any fancy name that you want, open parentheses, and then you can just use whatever you want to use. You can print whatever you want to do. You can add things up. You can have a summation. You can also have some arguments that you put into your function that will solve your whatever you're wanting to deal with in your pre or post-processing steps. And then in the end, to call the function, you use its name followed by parentheses. So this is just something, a very simple example, but just be aware that you're still able to use Python. You're not stuck in the Gurobi thing. You are working together with both of the capabilities. And I think you should make use of actually being able to use a full-fledged programming language in addition to your optimization software. And then finally, I still have another slide on the multi-dicts in case they weren't that clear within the example. So basically the multi-dicts that you're only able to use when you already imported the Gurobi Pi module, they will be helpful when you deal with large and complex input parameters. And the function basically splits a single dictionary into multiple dictionaries. So the input dictionary that you put into the multi-dict function maps each key to a list of n values. For example, you can think of an English dictionary that has English words on the one hand, and then on the other hand, it has 3 different translations. So it will have a French word, a German word, and a Turkish word for each of the English words. This is confusing. It's very helpful because you can translate a lot of things, but it will be a bit tedious. So you might want to throw this huge dictionary into your multi-dict function, which then will return to you a list of the shared keys, so a list of all the English words, and then n individual Gurobi tuple dictionaries, which means that you will have an English-German dictionary, an English-Turkish dictionary, and an English-French dictionary, but you won't have all of them mangled in together. So I think that's helpful to deal with different input and with different data types should you need those. But I think that this is a very smart way to actually be able to merge and unmerge large input parameter sets. And then finally, I have a nice list of links for you. The first thing is something that I stumbled upon on the internet while researching for what actually does Gurobi do. It's a Forbes article on what our world would look like without mathematical optimization. It was written together with some people from Gurobi, and it just paints a very sad picture of the world without mathematical optimization, and also a way less optimized and way less efficient world. And then again, I keep raving on about the Gurobi resources, but I still think those are one of the main ways to teach yourself Gurobi and to dive in deeper if you find things interesting. For example, you will find case studies and tutorials. You will find actual functional code examples. So if you have a very basic model, for example, a traveling salesperson problem, you will find functional code examples that you can just use and then adapt to your problem. And then as well, you will find some Jupyter Notebook modeling examples, which are dedicated within the Jupyter Notebook way of explaining things, of presenting things, and you will already be used to seeing Jupyter Notebooks because that's the way that we communicate Python to you. So I think that's a good approach as well to find some additional insights. And then finally, I will present 2 exercises to you that were adapted also from the Gurobi resource website. And we will be sending you into breakout rooms, as you already know from last week. And you will be discussing and coding and talking about the first 2 of those exercises. And the third one is a bit more actually of modeling work. So you will still be having to think about the model. And then it will be a bit more of implementation work as well. So this will be your homework or something that you can work on should you be interested in it. And obviously, we will present the key to you later on, and we will send the key to the third exercise as well to you in the realm of this presentation. So I will just quickly talk you through the 2 exercises, and then I will hand over to Rose again to do all the perfect magic of sending people into breakout rooms. So let's start with the first exercise. This is a problem formulation that is adapted from the example 19 from the 5th edition of Model Building in Mathematical Programming, which is a very nice source of seeing different models that are being programmed. It's just an introduction into general modeling problems that you will encounter throughout your periods in academia and throughout your life as an optimization expert. So the supply network design in this case, we have 6 end customers. All of them demand a product. The customer demand can be satisfied from a set of depots or directly from a set of 2 factories. Each depot has a maximum volume of product that it can support, and each factory can produce a maximum amount of product. We have costs that are associated with transporting the product, either from a factory to a depot, or from a depot to a customer, or from a factory directly to the customer. Our supply network has 2 factories in Liverpool and Brighton, and those have maximum production capacity as listed in the first table. The product can be shipped from a factory to 4 depots, and each of them will have a maximum throughput, which is listed in the second table. Then finally, our network has 6 customers, and each of them have the demand listed in this table. Then we have costs. So the shipping costs are given in the following table. The columns are the source cities and the rows are the destination cities. So you will see that we here also have the destinations of the customers. If there is no value, you won't be able to send from this to that destination. How can we satisfy the demands of the end customers while minimizing our shipping costs? So this is the overall problem setting. And in the following, it's the mathematical formulation that I don't think I will talk you through in detail, because you will be able to see that in your files as well. And should you have any questions, you can just come back and ask us so we can talk about that. Should it be the modeling or should it be the implementation? So basically you have the sets and indices of the factories, the depots and the customers. You have some parameters. Then you have the decision variable, which is the quantity that is shipped from a source to a destination. Then you want to minimize your total shipping costs, which is the product of the costs times the flow. And then you obviously have some constraints. As we already talked about, the factory cannot output more than its capacity. The customer demand needs to be fulfilled. The flow into a depot equals the flow out of the depot, because the depot is only a place that actually changes flows or redirects them, and it doesn't produce anything itself. And then finally, each depot must respect its capacity. And now the questions to you are how you can use Gurobi and Python to formulate the model. There is some hints in here. Basically, when you set up input parameters, already think about what you will be using those for. And then maybe multi-dicts are helpful for the data input. Hint, hint. And then additionally, when you refer to customers, depots, or factories, you can use some characteristics of the data type that you stored the input in when you did that in a smart way. And then in addition to formulating the model in Gurobi and Python, maybe you can also ask yourself how you can determine the optimal supply flow plan. And then the second problem that we want you to have a look at is a facility location problem, where you have a large supermarket chain in the UK that wants to build warehouses for a set of supermarkets. You already know where the supermarkets will be, but you have not determined where to set up the warehouses. You do still have some candidate locations where to build the warehouses, but you don't know how many of them you want to open up. Basically, you will have a trade-off between minimizing delivery costs. So should you just put a warehouse directly next to the supermarket, and to each supermarket, the delivery cost will obviously be very small. But then you have costs of building the new facilities. So each warehouse will have a lot of fixed costs to it. So you don't want to just put a warehouse next to each supermarket. Basically, you need to trade those two things off. Here we have 2 supermarkets and 9 possible warehouse candidates. The 2 supermarkets are set into those 2 coordinates, and the warehouse candidates are at those coordinates, and they're all related to these fixed costs as explained in the second table. If you want to transport any goods from a warehouse to a supermarket, the cost per mile is 1 million British pounds. The model formulation, again, is something that probably, maybe you already know, maybe you need to read through it, but I won't read everything out to you now. Overall, the decision variable is, there's 2 decision variables. On the one hand, the binary variable, whether you select a candidate location or not, and then the continuous variable that determines the fraction of supply that each customer receives from each facility. So translated to our setting, the number of demand that each supermarket receives from each warehouse. Then you want to maximize the trade-off between the cost of building a new facility and the total delivery cost over the 5 years. So the 1 million British pounds is such a large amount because it's already assumed that you're dealing with this setting for 5 years. And then, of course, there's 2 constraints, that the demand needs to be fulfilled, and we can only ship from facilities that have actually been built. So basically, we want to carry out the optimization and find a solution that minimizes our total cost. And we want to determine a warehouse build plan. So we want to print out something that we can show the company where to actually build their warehouse. And then maybe also something like a shipment plan would be insightful, which shows us the percentage of shipments that are sent from each facility to each customer. So I hope this was just a quick introduction to the modeling problems that we want you to have a look at. And I think that with any question you have, you can always come back to us, but Rose will have more insights on how to proceed. So thank you very much. Yes.
Thank you, Christina. I hope it was clear for everyone. So just like last time, we're going to send you into breakout rooms. So I'm going to go ahead and create those for all of you. And yes, so basically you can head on to your room as of now. And if you have any questions, don't forget you can always call us to your room, or you can come back to the main room just by hitting the button leave room. Okay? So happy optimizing.